Hello, I and Ananya. We are a team in EW2 project for the second project, and we are asked to build a RC meter where R meter is the resistance meter and C meter is the capacitance meter. Resistance meter is basically measuring the resistance, and capacitance meter measuring the capacitance. Now these are the contents we have in our slides: motivation, preliminary design, main challenges we have faced, block diagram of the different circuit, and whatever the approach we took in our building the project. Now working on the circuit, then final circuit and test results, and then the conclusion. Now this is the motivation behind this making this circuit. Basically in our lab, capacitor meter is not readily available, so we are trying to build a capacitor meter, and along with that we are also making the resistor meter, because mainly the precision factor is there, so we try to build a resistor meter with some higher precision and accuracy. Now this is the block diagram for our preliminary design. We tried to build a resistance and capacitance meter by this circuitry. Here we tried to give some sine wave as an input to the BIMC. This is our basic impedance measurement circuit, and then also we are giving the sine input to phase shifter to shift it by -π/2. Now whatever the output we have in BIMC and phase shifter, we are giving that to analog multiplier. Analog multiplier basically multiply both the input given to it and then passing it to LPF. LPF is a low pass filter, and then the output voltage is just somehow output voltage is relating to the resistance and capacitance. So we are doing the reverse calculation, and we are getting the value of R and C from there. So this is our preliminary design, and this is the LT-SPICE simulation we did for this preliminary design, and it was working well in simulation. Now what are the challenges we faced in our preliminary design? We have too many blocks for the preliminary design, that is quadrature oscillator, analog multiplier, and then thereafter we have also LPF. So there is problem that even there is a small error from any of this block, the whole circuit will give error. So this is one of the challenges we faced. Now what are the individual error from each block? Quadrature oscillator, basically there is a mismatch between cos and sine wave. There is mismatch between the amplitude we are passing to the amplifier multiplier circuit from as an output from the quadrature oscillator. So there is an error involved in quadrature oscillator, so we are also ending up with error in analog multiplier. That is one of the issue. Then analog multiplier is a pretty difficult to design hardware. It was not giving correct output for the negative inputs, and it was not multiplying the two inputs given to it accurately. That's the major problem in our analog multiplier. Then circuit complexity is also one of the issue, because what I mentioned earlier, that there is a lot of blocks involved in this circuit, so even there is a small issue, we will end up with a larger issue at the end as an output. Now we are talking about the improvement. So we left that idea and improvised our circuit. This is basically a amplifier, instrumental amplifier. It involved 3 op-amp. So here this is the output. We are giving 2 inputs from here. Now this is giving output as a some constant multiplied with some resistance value, and this difference between these 2 input. So we are searching for a circuit that combine the output as a constant times some resistance. So here output is voltage into resistance. So we got this circuit. This is also easy to implement in hardware, so we forwarded with this circuit. And here you can see the total output. It's a difference between these 2 inputs, and the gain is equal to R2 by R1, and this RG is the test resistance we want to test, and this is resistance. We have to, accordingly the resistance we want to measure, we change this resistance RFB and RF to RFB, both are same. And we also, to simplify the circuit, we just R1 we took the resistance same values, and here R2 and R2. Now this is the working of the circuit. Basically we are giving input from this to end, and this is the test resistance. This is R1, this is also R1. So these two resistance are the defining the range what we want to measure. Accordingly, the resistance we want to measure, we are changing this R1, and here we are receiving the output. Now we are this is the calculation, hand calculation we did for this resistance. Now you can see this is V out. The formula is suggesting minus Vt plus 1 by 2 R1 by Rg. R is the test resistance. Minus V2 is basically because we are not giving any input to V1. So V1 minus V2 is the difference between two input resistance become minus V2. So ground V1 is grounded here. Now we chose the V1, V2 is around 1.1 because here the R3 by R2 here from the last result you can see V out is equal to minus R3 by R2 1 plus 2 R1 by R gain. Now we chose V input is equal to 1 because we want to measure we want to show the result in using Arduino. So Arduino basically can measure from 0 to 5 volts. So we want to take the range from 0 to 5. That's why we gave 1 is an input voltage, because the small the value just greater than 0 also will work for, but the problem is that Arduino can't measure above than 5. That's why we took the voltage 1 as an input. Now these are the ranges 4K and 10K, 10K to 100K, this is 100K to 1000K. We have to accordingly change the resistance R1 I mentioned earlier. So we have to change and we'll measure the circuit.
This is the capacitance measurement circuit that we have made, and the block diagram goes like this. Two of the most important components in this are the 555 timer that we have and the CD402C counter. So the inputs to the 555 timer we are giving are one trigger and the test capacitance that we want to test. And for the counter we have a clock from WaveGen which is giving a given waveform with a given frequency, and whatever output that we get from this counter we are giving it to 7-segment display so that it can display us the value of the capacitance. So this is how it works. So let me first explain how 555 timer works. So 555 timer, here we are running it in the monostable mode. So it triggers whenever we are giving it a negative going pulse. So here we can see the trigger that we are giving here. This trigger is a negative pulse. So whenever we give this negative pulse, as we can see here, this monostable counter starts giving an output, and then output is nothing but it is a pulse that will remain high until and unless the R1 C1 network, that is the C1 that we are giving here, the C1 that we are giving here and the R1. So unless and until this charges to up to 0.63%, this will give a high value, and once it is charged to up that percent, it will start giving a low value. So the amount of time for which this 555 timer will give a high pulse is 1.1 into R1 into C1, that is the time constant. So the output of the 555 timer, the output pulse that we are giving, that is given as an input to a counter, and that is having a clock time period which we are giving from the WaveGen. So the output of the 555 timer goes as an input to the enable of the counter. So as long as the 555 timer is high, this enable is on so that the counter keeps on counting. So once the 555 timer gets off, the enable also is off and the counter will stop counting. So essentially the counter will give us the time taken by the 555 timer to remain high, which is indirectly the time taken for the R1 C1 network to charge. So based on that ideology, we can see the time constant is 1.1 R1 C1. So until this time, the counter will count and will give us how many seconds or the time taken for it to charge. And now let X be the number displayed on the 7-segment display. And the time calculated by the counter will be X into Fs. Fs is nothing but the frequency of the waveform that we are giving to the counter. And time constant, as we know, is this. So by calculating all this, we get this equation that the capacitance is equals to X into Fs by 1.1 into R1. So in this way, we can very easily, using a counter and just a 555 timer, measure the capacitance of a circuit. And we have varied ranges for measuring the capacitance. So first is we can measure 1 pico to 999 pico. But for that, the input that we are giving to the counter as a clock, that frequency must be 1 megahertz. So the calculation for this is also done. So what we have basically put in mind is for each count, that whenever the counter represents 1, we want it to represent 1 picofarad. So the range in which the counter has to measure, that is the time taken, is 10 power minus 3 to 10 power minus 6 as the frequencies. So we chose the frequency as 1 megahertz, and based on that, every single count of this counter will measure 1 pico. Similarly, we have done things for both of these two, and calculations are shown here. So every one count will measure 1 nano, and every one count will measure 1 micro here. And the frequency required for nano is 1 kilohertz, and the frequency required for the micro range is 1 hertz. So these are like, so essentially the range for an entire capacitance meter is from 1 pico to 999 micro.
This is showing the result of the capacitance meter. Now this is the entire hardware circuit. So this is showing 58 nano. Now we are going through the test result of the resistance meter. Now these are the all of the results we obtained from the lab. Now this is showing, you can see 67K from here, and from the multimeter you also can see that this is 67.2K. So it's pretty much close, and accuracy is also good, I think. Now again you can see from here also, this is 26,418, so around 27K, and we can also see from the multimeter that it is 27K. Here it is 39,430, and this is 37.95. It is pretty much close, and this is 95K, and this is 90.5K. So somewhere, if you are increasing the value of resistance, the precision is little bit low, so we are going like this. Now these are all the values we are also getting. You can see from here, from the slides, this is 26K, it's around 27K. So 500 ohm is the only difference here. So it's good in everything. Now you can see the test results of capacitance meter in the next slide. This is showing 88 nanofarad, and this circuit, hardware circuit, is also showing some 97 nanofarad. So there is a gap of some 9 to 10 nanofarad, and in measuring those values, I think we will have some problem with multimeter also here. So it's not also accurate. So I think this is pretty close, and the accuracy also is good. Here it is 58. It's showing 48. Here it is 519, and it is showing 418. So 418 picofarad, and this is 516 nanofarad, picofarad. Sorry. So it's showing somewhat close, but not that much. So whenever we are measuring the capacitance for picofarad, we are involving somewhat more precision issue. These are the proposed improvement and constant. Aruna will explain this.
So coming to the improvements and constraints, the very first improvement and constraint that we could talk about is the precision, both in capacitance and resistance. So here we would like to measure our error rate. So error, as we measure from experimental results, is like 3 to 5% in resistance circuit. But this 3 to 5% is before attaching the Arduino. Like if we just take the output voltage that we are getting from an analog circuit, we do the manual calculations, we are getting only a 3 to, actually precisely to say 3.3% error. But when we are adding the Arduino, because of the issues in taking the inputs, because of the sampling rate and other issues, we are around getting 10% of error. So like our overall resistance meter has a 10% of error. And coming to capacitance meter, because of the delays in the counting or counter, or because of the delay in the NOT gate also that we are having a little issue in the counting, because of which we are having like 7 to 10% error. And coming to the second improvement is range ambiguity. So as we explained earlier, whatever measurement we were doing, we were like in resistance circuit, we were setting the R1 resistance based on the range. So unless and until we know the range of the resistance, we can't really measure it accurately in a circuit, because we don't know which R1 value to choose. Similarly, in capacitance circuit, we were choosing frequency based on capacitance ranges. So whenever we have to check for a capacitance or resistance value, we have to know which range it falls in, like whether in nanofarad, picofarad, etc. And the third improvement or constraint that we could talk about is Arduino measurement. Arduino measurement, because it's a digital circuit, it has various factors, like it has sampling factor, and our code also works in such a way that it has to take the maximum, because we need the amplitude, and from the sine wave generated we have to pick out the maximum amplitude. So sometimes what happens, when it doesn't sample at that maximum frequency, we cannot really take the maximum amplitude from there, and that was a little issue with the Arduino. So maybe if we could have a better microcontroller which could take more accurate results, then we could have reduced the precision errors. So this was our circuit. So in conclusion, these resistance and capacitance meter circuit, like, it has been a quite valuable learning experience for us, because the circuit that we have taken is not something that was available on internet, especially for the capacitance, and it was something that we had to design and build from scratch. So we actually learned a lot of fundamental concepts here, fundamental electronic concepts. We learned about the 555 timer, about what the amplifier is for measuring a resistor. We also learned about counters, how they work, the different modes of a 555 timer, and we also learned how to set the precision ranges. And coming to hardware also, we learned a lot of things as to how to make the hardware more efficient and how to choose shorter wires or whatever. So it finally gave us a hands-on experience on a real-time project that could be used in real time. So it is like, if we could make a little more improvements to this is easily deployable also. So I think this project gave us a great experience, and we thank all the mentors, instructors and the teaching assistants of this project, of this course, because I think it was a valuable experience for us.